Welcome to Topology sessions. Today we will discuss what is the meaning of topology, the word, and what is the relation connecting topology, geometry, etc. So we are starting with motivation for topology. The third section in your first chapter, motivation for topology. So our topic name is topology. So what is the meaning of topology? Topology means which can be split up into topos and logos. Now, topos means surfaces, logos means study. So, topology as a whole means study of surfaces. Okay, so topology means study of surfaces. Now, we can examine what's this relation with geometry. But before starting that, we want to know what is a geometry. So I'm writing here geometry. What is it? What do you mean by geometry? Which means the study of, the word meaning is, uh, as we have started in topology, it can be split up into geo plus metry. Now, geo means something related to earth. Related to earth. And metry means measurement. Metry means measurement. Now, geometry means the word meaning is measurement of earth. Word meaning is measurement of earth. But the actual meaning of geometry is like this: study of geometric properties of objects. So, geometry means study of geometric properties of objects. Now, again, we want to know what is a geometric property. So, geometric property. So, what's a geometric property? Some of the examples are, can you list some of the examples? Yes, area, volume, length, curvature. Lots and lots are there, we have to list it out. Okay, I'm listing some of them. Now you can see that these properties are invariant under congruence. So we can say that the geometric properties are those properties. So geometric property are those properties which are invariant under congruence, which are invariant under congruence. Now, what is congruence? You can see the definition of congruence. Definition of congruence. Two objects, A and B, are said to be congruent to each other if there exists a bijection f from A to B which preserves distance. That means, suppose you are having two sets here. One I am naming it A and this is naming as B. Now we want to have a bijection F from A to B. And suppose I am taking 2 points over here A and this is B. So correspond to this, I will have here one point f of A and here I will have a point f of B. Now if you are measuring the distance between A and B, it should be the same as the distance between f of A and f of B. Then we will say that this preserves the distance. So preserves distance means distance generally we will denote it as d of. So d of A comma B should be same as d of f of A comma f of B. If you are having such a relation, then this relation is called a congruence relation. I repeat, a congruence relation is a bijection which preserves distance. If this is true for every A comma B belongs to A, then we will say that A and B are congruence. Congruence is another name is isometry. Okay, congruence or another name is isometry. These two are the same. Thus, a property is said to be invariant under or preserved by congruence if whenever an object has that property, so does every congruent to it. Note, this congruence preserves distance. This congruence preserves distance. That is, congruence preserves anything which is related to distance. Okay, So congruence preserve distance that we already discussed. That means congruence will preserve anything which is related to distance. Now we are moving to geometric properties. As I said, geometric property means those properties which are invariant under congruence. So geometric properties. Geometric properties. Those properties which are invariant under congruence. Invariant under congruence. Now we have studied set theory. Now set theoretic property means which are invariant under bijections, and group theoretic property means which are invariant under isomorphisms. So these are the two things we have studied previously. I repeat, set theory, we have studied set theoretic properties. That means those properties which are invariant under bijections. So set theoretic property means invariant under bijections. Bijections. Next thing we have studied is group theoretic properties. Group theoretic properties. So group theoretic properties means those properties which are invariant under isomorphisms. Isomorphisms. So these are the two we have already studied idea. Now we can examine what is the relation connecting geometry and topology. So geometry and topology. Definition. We are examining first of all what's the definition for continuity. Okay, so continuity definition is making use of the idea of distance. Let A and B be subsets of Euclidean spaces and F from A to B a function and x naught belongs to A. We say F is continuous at x naught, F is continuous at x naught if for each epsilon greater than 0 there exists some delta greater than 0 such that such that d of f of x comma f of x naught is less than epsilon for all x belongs to A, for which d of x naught is less than delta. This is our usual definition of continuity. We will say that a function f from A to B is continuous at a point x naught belongs to A if for uh, for each epsilon greater than 0, there should exist a delta greater than 0 such that the distance between f of x and f of x naught is less than epsilon for all x belongs to A whenever distance between x and x naught is less than delta. And we say f is continuous if it is continuous at all such points. And we say f is continuous if it is continuous at all points of A. Our usual definitions. Now these continuous functions are somewhere called a map node. A continuous function is called a map. Continuous function is called a map. Now our question is, if f is continuous, bijection, then will f inverse, if f is a bijection means definitely you can go for f inverse, then will f inverse be a continuous function. So try to get an example for this. So I'm leaving for you to work. What you have to do is you have to come with either an example such that f inverse is not continuous, or you want to prove that if f is a continuous bijection, then f inverse is also a continuous function, a continuous bijection. So I'm leaving this for you to work. Next we are moving to a definition, homeomorphism. Definition, homomorphism you might have studied. Here we are using homeomorphism. Don't get confused with homomorphism. It is homeomorphism. Homeomorphism. So homeomorphism. Let A, B be subsets of Euclidean spaces a homeomorphism from A to B is a bijection A from A to B such that both A both F and its inverse are continuous are continuous. So this is the definition of homeomorphism. Let A comma B be subsets of a Euclidean space. A homeomorphism from A to B is a bijection, and F from A to B such that both F and its inverse are continuous. Such a map is called a homeomorphism. Or else we can say in another fashion like this. As a note, we can write it as note a function f from A to B is a homeomorphism is a homeomorphism if and only if there exists a continuous function there exists a continuous function g from B to A such that the composite G composition F and F composition G are equal. When such F exists, we say that A and B are homeomorphic to each other. So not 2. So that make this as not 1. So not 2. When such F exists, we say that A and B are homeomorphic to each other. Now, second question for you is to work is homeomorphism is an equivalence relation. So we can show that homeomorphism is an equivalence relation. So do it by yourself. We want to show that homeomorphism is a reflexive, symmetric, and transitive relation. So I'm leaving for you to work this as a homework. Thus, the comparison of geometry and topology will lead to the comparison of congruence and homeomorphism. So, in order to the comparison of thus the comparison of comparison of geometry and topology leads to the comparison of congruence and homeomorphism. And homeomorphism. Thus, the condition that all distances be preserved trivially implies continuity, right? So, homeomorphism means we will say that both f and f inverse should be continuous. Now, congruence means we are saying that it should be a distance preserving bijection. So, distance preserving bijection should be always a continuous function, right? So, need to say that the condition that all distances be preserved trivially implies continuity. Thus, the condition that all distance be preserved trivially implies the continuity. Thus, we can say that when a geometric or the geometer is looking at these two properties, for him these two should be equivalent. Or geometric classification of objects geometric classification of objects is stronger, or another name we can use that stronger or finer. I will put in this bracket. Stronger or finer than topological classification. Topological classification. That means when you are having a Venn diagram and all, means you can represent your topological properties and geometric properties like this. This one should be your geometric properties. Okay, I will use another color. This should be your geometric properties. And this should be your topological property. So, geometric properties for a geometer, this topological property and geometric property should be the same. Next question we want to answer is, Is every homeomorphism a congruence? So here we are having the idea every congruence relation is a homeomorphism. If that is every congruence relation congruence relation is homeomorphic. Now, what about the converse? So, another question is every homeomorphism a congruence? Is every homeomorphism a congruence? Let us treat it like this. Let we are having two rods. Okay, one I am naming as A, another I am naming as B, and this is of length. This is of length 1 unit. These are rods. Okay, and this is of length 2 units. 1 meter and 2 meter you can have. So we can express this in our mathematical terms as this is of closed interval 0, 1, and this is as closed interval. No need of taking 0, 2. You can have any interval which is having the length 2. That's all. So I'm taking as 2, 4. Now define a function f from a to b as f of x equal to 2x plus 2. Is it continuous now? Yes, definitely, because a polynomial function, right? So it should be continuous. Then f is continuous. F is continuous. And its inverse when you're taking g from b to e. What should be its inverse? We can easily find out for this is substituting y equal to 2x plus 2, and we can go for x equal to. So we'll get this x equal to 1 by 2 into y minus 2. Am I right? So we can have g as g of y is equal to 1 by 2 into y minus 2. Okay. Now this is also continuous because again it's a polynomial function, comma, which is also continuous. Which is also continuous. Thus f is a homeomorphism. Thus f is a homeomorphism. Thus this f is a homeomorphism. Thus A and B, thus A and B, what was our A and B? A means a rod of length 1 meter. 1 meter, you take it as 1 meter. And B means a rod of length 2 meter. Thus these two two rods having different length are going to be homeomorphic. That is A and B are homeomorphic to each other. Even though congruence means it should be distance preserving, but we are having one length rod is having length 1 unit and another rod which is having length 2 unit, so the distance are not equal. Okay, so even though it is not a congruence one, right? Congruence one. So the reverse implication is not at all applicable. So this is the thing we want to discuss here. See here, we have taken two rods of different length. One is 1 unit and the one is 2 units. Now we can form a homeomorphism between these two, even though it is not congruence. So what is the operation we have did here? We have taken f of x equal to 2x plus 2. That means a 1 unit length rod you are extended to a rod of length 2. Thus this operation, that is uh, the operation means stretching. You are stretching your rod to double the size, or just you can take G as shrinking, or shrinking the rod of 2 units length to a rod of length 1 unit. So these properties are not affected by the homeomorphisms. Okay, so we will have a note here. Thus, so what should be the operation which may affect your topological properties? Here you have taken a rod of length 1 unit and you are stretched it, right? From here you are extended, from here you are pulling it, right? You're pulling from this side and this side. You will get, this will convert into a rod of length 2 units. Okay, now when you want to shrink it means, suppose I am taking a rod of length 2 and just I am shrinking from this side and this side. If I am exerting pressure, I will get this rod will convert into a unit length one. This is 2, this is 1. So these two should be, as we have seen, these two should be homeomorphic. But what will happen if I am cutting this into 2? That means this rod I am cutting here. So I will get two rods, right? In that cases and all, it is not to be homeomorphic. Thus, we will list out some of the operations which changes the topological properties. Thus, operations which changes which changes topological properties topological properties are, first operation is cutting. As I said, cutting the rod into two. Second one is gluing. Gluing means you take two objects, then stick here. These two you are sticking. Just you take paper strips and all, and put some gum over here. Just you paste it these two. Now when you are pasting these two means, see here it should be an overlapping will come, right? So at that point our topological properties will not hold. So gluing. Another one is piercing. Piercing is cutting a hole. Piercing. So when you're having a disc over here, just you having a hole here, it won't be isomorphic to this disc. Sorry, not isomorphic, it's not homeomorphic. So piercing and cutting a hole. Cutting a hole. So these are some of the properties. You can have lots of operations. I'm listing some of them over here. So with this, you can see an interesting fact like this. Suppose you are having a definite or a torus. Okay, just a torus you are having, and you are having a teacup. Suppose you have got a teacup here. Okay, next you are having a needle, stitching new needle. So as you know, so this is the needle. So when you're having these three items, for a topology expert, these three are going to be the same. Same for a topologist. Same for a topologist. Okay, how we can say that these three are same for a topologist? That means first you take this torus. Okay, using a different color. Okay, okay. You take this torus. Okay, now suppose you are extending from one side. Okay, so torus, I'm extending the torus. So I'm extending means I will get something like this. Okay, this side little bit thick. Okay, now just suppose you are having this as a rubber sheet or something. So you can have here something like this picture you will get. Then again this cup also you can extend to this side. You'll get only one hole here, right? And this needle, see, from here to here the journey is very simple, right? We are finding from here to here means very simple, right? So like this you will get, from this you can again go for extending it. So you will get something like this, right? Then again go for stretching it. You'll get from this to this. Okay. Now from geometry to metric spaces. Metric space also we are having the distance relations, right? So here just you want to note two definitions that you have already studied. One definition is what do you mean by metric space? So just you brush up your metric space idea, metric space definition, and another one you want to brush it up is that uh, convergence of sequence. Convergence of sequence. So read these two and come for the next day's class. Okay, with this we can go for, these two are going to be the basics of what you're going to discuss in your next class. So thank you for your patient listening. I'm winding up today's session here. Thank you.